All right, today we are going to talk about dividing monomials. This should look pretty familiar for the most part. So we are going to simplify quotients of monomials and find the GCF of several monomials. To review, we need to write the prime factorization for these numbers. In order to write prime factorization, what do we need to make? A factor tree. So I'll do that off to the side. Create a little bit of blank space. If I'm going to write the factor tree for 42, what's something I could break 42 into? 2 times what would give me 42? 21. So 2 times 21 would work. You could also use 6 times 7. We could break 21 down further into what? What times what would equal 21? 7 times 3. Okay, just as a refresher, what number never goes on our factor trees? A 1 never goes on our factor trees. We stop when we have prime numbers. So 2, 7, and 3 are all prime numbers, so we know we can stop. Any number that we broke down, we are not going to use when we write our prime factorization. And remember, we write them in numerical order. So which number should I write first? 2 times 3 times 7. Okay, so that's our prime factorization. For the GCF, yes, but they only gave us one number, so we can't find a GCF unless we have more than one number. All right, now we're going to do the prime factorization of 56, so I'll make that tree on the other side. What could I break 56 into? Two numbers that would multiply to 56. Okay, 2 and 28 would work. 28 would break further down into what? Liam? 14 times 2. 14 will break down into 2 times 7. Good. So what would our prime factorization be for 56? Very good. So we had 3 2s, so 2 times 2 times 2 times 7.
Can you put 2 to the third power times 7?
Sure. If you would rather write it as 2 cubed or 2 to the third power times 7, that's fine. Number 3 kind of leads in from 1 and 2. What's the GCF of 42 and 56? So when we look for GCF, we make those prime factorizations, and then we look for our matches or our pairs. So what matched from those lists? 2 and
7.
2 and 7. So we would cross off a 2 and a 7 from each list. Those are the only things that match up. And 2 times 7 is 14. So that's our GCF.
So they don't have.
What are the positive factors of 48? So when we're making a list of factors, what do we start with? 1. Good. So I'll write that down here. 1 times 48. Then we would move on to what? 2 times what pairs up with 2? It's an even number, so I agree it's divisible by 2. We gotta think about what pairs up with 2. Liam, what do you think? 24, good. Is 48 divisible by 3? How do we check?
Was there some like 1 into it? Oh no, never mind.
Our divisibility rules we did on Wednesday last week. Has to do with the integers here, 4 and 8.
You have to add up to something that's divisible by something.
You're on the right track. What would 4 and 8 added together be?
12.
12. Is 12 divisible by 3?
No.
Yeah, so that means 48 is as well.
So it's 4 and
Not 4. It's 3 and... Thought somebody said it. How many times would 3 go into 4? How many times does 3 go into 4? Once. 1 times 3 is subtract. Bring down your 8. How many times does 3 go into 18? How many times does 3 go into 18? 6. So 3 times 16. Next, after 3, we would need to check 4. 4 times what? 12. After 4, we check 5. Is 5 going to work? No. So after 5, we check 6. 6 times... 6 times what? 8. After that, we check 7. Would 7 work? No. Okay, so then we move on to 8. Do we need to do 8 again? No, so we're finished. This would be our full list. Now, the tricky part about 4 and 5. 5 asks what are the positive divisors of 48. Well, we just found all of them. It's the same list. So the answer for 5 for divisors, that would be the same exact list. Those factors are also divisors. They divide evenly into 48. Questions about these 3 types of problems from last week? Okay, we'll move on. All right, some of these properties you will probably already be somewhat familiar with. If A, B, and D are real numbers with B not equal to 0 and D not equal to 0, then AC over BD is equal to A over B times C over D. This is probably just listed backwards from what you normally would have seen. If you're multiplying fractions together, you multiply the tops together, you multiply the bottoms together. That's all this is saying. The whole A, the B and D not equal to 0 is just because you can't have 0 in a denominator. It's the only reason it's written there. Okay, so when we simplify these quotients, the whole reason they gave us that slide, I'll write it out in a little more detail than you probably would if you were doing this on your own. I could break 15 into what times what? 5 times 3. And I could break 21 into... 7 times 3. Okay, so if I'm using that property from the last slide, I could break these up. Right? My top was 5 times 3, so I split that up. My bottom was 7 times 3, I split that up. What do you know about 3 over 3?
1.
It equals 1. So 5/7 times 1. Anything times 1 is
5, 7.
itself, so it would just reduce to 5/7. It's just a different way of writing something that you've already learned before. Okay, you should already know how to simplify fractions. This is just a different way of writing it. So, for example, on number 2, I could rewrite 20 as 4 times what? 5. And I could rewrite 48 as 4 times 12. And 4 over 4 reduces to be 1. And again, 1 times anything is just whatever that thing is. So 5/12 is what this would simplify or reduce to.
Do you want us to simplify now? The thing will be simplified?
This is as far as they can go. But yes, that's the whole idea here, is just simplify as much as possible. Okay, this should be a review, right? Questions about it? You don't necessarily have to be able to write it this way, but this is just showing that property. You are going to have to be able to simplify fractions or quotients. All right. So another property that you should have seen before. If B, C, and D are real numbers, B is not equal to 0, D is not equal to 0, then BC over BD is equal to C over D. What did they do here?
Swapping.
What canceled out?
The B and the B and the B.
The B's canceled out. So they're just showing that we could reduce this or cancel out those B's to get us just to C over D. Okay.
So you want us to
Nothing.
put reduce? Or
Nothing new here. That note.
remember?
Yes. Remember, if the same number or variable is in the numerator and denominator, they will reduce. Today should be an easy lesson because it's very similar to stuff we've already talked about. The only slight difference is when we get to the GCF stuff. But technically, we've already divided monomials to a certain extent. All right. I'll give you a minute to simplify these on your own if you have not already done so, and we'll talk about the answers. What did we get for number 3? Austin, what'd you get? You don't know what 35 and 42 are both divisible by?
7.
Okay, what's 35 divided by 7? 5. And what's 42 divided by 7? There, so you should have gotten 5/6. If you wanted to write it as times 7 over 7 like we were doing before, you could do that. I'm not requiring that, but if you need to see it, there it is. Any volunteers before I pick somebody for number 4? Dominic?
Negative 2 over 5y.
I think you're close. Where should the y go? Top or bottom? Top. Good. So negative 2y over 5. It does not matter to me if you want to put the negative sign out in the very front of your fraction. But the y should definitely be in the top. So the x's reduced or canceled out the 4 over 10 reduced to 2 over 5. Questions about 3 or 4? Okay, we'll move on. This is a rule that we already should have known from before. We've talked about this rule. If we're dividing exponents, what do we do to them? Subtract. So when you divide the same base, you subtract the exponents. That is not a new rule. Did we get that filled in? You got an equal sign right there? Okay. The next one is if n is greater than m, then technically you end up with 1 over a to the n minus m. Now, I'm not a huge fan of this rule. I like it better when we just do it the same way every time. And then if your exponent is negative, it has to get moved. So if you want to stick with that, that's fine. It ends up being the same as this. I think this is just getting a little picky. The next one, if n and m are equal, then m minus n would be 0, and anything to the 0 power is really just a 1. Okay, so I would maybe put a box or a star by that top rule. That's the one that I would go by. This one. But if you get a negative exponent, then you're just going to have to deal with that. Getting a 0 exponent, you should already know how to deal with pretty easily. So let's move on to some of our examples. Again, this should be a review. What are we going to do here? Do what with our exponents? Subtract them. So we're taking what minus what? 7 minus 4 is 3. So we get a to the 3rd power. Positive exponent doesn't need to move. That's it. Remember doing this a couple weeks back? We've already taken a test on it and everything. All right, on this one. Again, we subtract our exponents. We're taking what minus what? Okay, 3 minus 8. 3 minus 8 gives me a negative 5, but I don't want a negative exponent, so I need to... Okay, so we could put it over 1 and then flip it. And when we flip that down to the denominator, the 5 becomes positive. Remember doing that? Okay, the other kind of trick or rule to remember it by is wherever the bigger exponent is where your variable is going to end up with its positive exponent. So the 8 was bigger, it was on bottom. X to the 5th ended up on the bottom. On the last one, a to the 7th was bigger, and that was on top. And our variable a to the 3rd ended up technically on top. You could have put it over a 1. All right, number 7 gets a little interesting. We need to simplify this. An exponent outside of parentheses. How do we handle that? It belongs to what? What about the top? Well, we do have a negative 1, but I want to focus on the 9 out here. What does it belong to? Good. Everything inside the parentheses. Does it belong to the negative? No. Okay, so we could rewrite this. You could put it as a negative 1 if you wanted to, times x to the 9th times y to the 9th. And in our denominator, does the x have a 9th power? Why does this x not get a ninth power?
I'm not parentheses.
There's no parentheses, so this one's just x times y to the ninth. What is going to cancel out nicely?
With 2 exponents.
The y's. Why do the y's cancel out nicely? Why do the y's cancel out nicely?
Doesn't all have the same exponent.
They have the same exponent, and if we were to take 9 minus 9, we'd get 0. Anything to the 0 power is 1. So if they have the same exponent, they are going to completely cancel out. All right, is there anything to cancel out or change the negative 1? Any other whole numbers? Integers? Is there anything to cancel out with that negative 1? No, there's not. So we know it will still have a negative or a negative 1. What exponent is on the x in the denominator? A positive 1. When we divide the same base, what do we do with the exponents? Subtract them. 9 minus 1 is 8. You could leave your answer like that, or you could just write it as negative x to the 8th. Either way is fine with me. Does it need to go in the denominator?
Yes. Wait, isn't it already?
No, because the exponent is already a positive. So I don't care if there's a negative out in front. I just care if the exponent is negative. It's not, so we leave it alone. All right. When finding the GCF of two monomials, you must circle both your number matches and your variable matches. So this is where today gets a little different from what we've done before. Everything else we've really done in our notes so far has been a review. This is where it gets just a little different. Okay, did we get those notes filled in? Finding the GCF of two monomials, circle your number matches and your variable matches. All right. Find the GCF of the two monomials. So we are going to handle the number part separate from the variable part. The number part is what we were doing last week, which means we need to make a factor tree for 72 and for 120. Give me two numbers that multiply to 72. Dominic?
2.36.
Okay, 2 and 36 would work. 2 is prime, 36 is not. 6 times 6 is 36, so I could write that down. Each 6 breaks down to 2 times 3. So if I'm writing out my prime factorization for 72xy, it's going to be 2 times 2 times 2. There were 3 2's. Times, how many 3's were there? How many, Liam? 2. 3 times 3 times x times y. Questions about where I got 2 times 2 times 2 times 3 times 3 times x times y. Okay, then let's talk about 120x squared z. Give me two numbers that multiply to 120.
11 times 10? No.
What?
Isn't 11 times 10? No.
10 times what? This should be easy. 12. 10 breaks into what?
5 times
12 breaks into what?
2. 6 and 2.
6 breaks into what?
2 and
Okay?
4. 2.
So we have 120x squared z. How many 2's did we have? 2 times 2 times 2. How many 3's?
1.
What else did we have? Okay, if we have x squared, that's how many x's? X squared is how many x's? 2 of them. X times z. So now we have to find our matches, both numbers and variables. What is one of my number matches?
2. 2 and 3.
Well, careful about saying all of them.
1, 2, 3.
Okay, so all the 2's match up. What else matches up?
The 2 3s.
These 3's. Do I have other 3's?
No.
No. What else?
2 X's.
X's. Anything else? No. So when I write out my prime factorization, I'm going to put 2 times 2 times 2, okay, for each pair of 2's, a 3, and also
X.
an x.
Would you put squared?
Would we put squared?
I mean, just say that amount of writing, can we put squared?
So we only put a squared if we mean to write down 2 x's. Do I want to write down 2 x's? No, because we only had one match. So we write it down for every match. So we had 3 matches of 2's. That's why I had 3 2's. 1 match of 3's. So 1 3. 1 match of x. So 1 x. Then we multiply it all together. So 2 times 2 times 2 times 3. Or 2 times 2 is
1,
2 times 3 is
6,
6 times 4 is 24, and then I still have x. So that would be my GCF of those 2 monomials.
Okay.
Not a whole lot different from what we did last week. We're just throwing in the variable part. Questions on 8 before we do the next one? Okay. This one, in my opinion, should go a little bit quicker. I don't even know that we necessarily have to show factor trees. What is 21 going to break into? '21 only has one factor pair we could possibly use. 7 and 3. So it's going to be 3 times 7 times how many x's?
3,
X times x times x times what else?
y.
1y. 6 can also only break into one set of factors. What times what?
3 times 3.
Okay, 2 times 3. How many x's?
6.
1, 2, 3, 4, 5, 6. How many y's? 1, 2, 3. Okay. After we have our prime factorizations, we're looking for matches. What do we have a match of? Match of 3's. What else?
So for the matches, matches, you only put it one time.
What?
You said per each one, you only put down one. So
Yep, so we would only write down 1, 3. What else do we have a match of?
1, 2, 3 matches of X.
Okay, 3 matches of x's, so I would have x to the
Third power.
3rd power. What else do we have?
1 match of Y.
1 match of y's, so 1y. So our GCF would be 3x cubed y. Questions, concerns? Finding the GCF? Okay, we'll move on.
Huh?
Yeah, I think that problem just didn't get updated, but that's fine. I can take it away and write down what we're supposed to have. Negative 24 x cubed y to the 5th z over 36 x y squared z to the 4th. Okay, this is a type of problem that you've technically seen before. Okay, we have simplified these types of expressions. Remember, the number part gets simplified kind of separate from the variable part. So when we start building our answer, we know that negative 24 and 36 are both divisible by what? What number could divide into both 24 and 36? If you're not sure, we can make our factor trees. What could I break 24 into? 2 and 12. 12 breaks into 2 and 6. 6 breaks into 2 and 3. We could also make it for 36. 36 breaks into what? 6 times 6. Each 6 breaks into 2 and 3. Okay, so if I'm looking at my list for 24, I'm looking at 2 times 2 times 2 times 3. And for 36, I'm looking at 2 times 2 times 3 times 3. What do I have matches of?
2 sets of 2 and 1 set of 3.
Okay. So 2 times 2 times 3 would be what? 12. So that's my GCF. So I could divide negative 24 by 12, and I could divide 36 by 12. So negative 24 divided by 12 would be negative 24 divided by 12 is negative 2. What about 36 divided by 12? 3. Okay, for all of my variables, if I'm dividing the same base, what do I do to my exponents? Subtract them. So x, we've got 3 minus 1. 3 minus 1 is? X squared. Do you think it'll end up in the top or the bottom? The top. The bigger exponent for x was in the top. That's where x squared is going to go. Next, the y's. 5 minus 2 is 3. So y to the 3rd should end up where? Top, because it already came out positive. For our z's. Very good. Z to the 3rd. It would end up on the bottom because the bigger exponent started on the bottom.
What if we just save that word and just did negative 24 and then 36 and then did that
Well, that's what I was hoping for the whole time, but nobody was speaking, so we had to do it this way. Okay, you should already know how to simplify fractions. That's not something that should be new to anyone. Now, it's easiest if you identify the GCF first. But if you hadn't identified the GCF first and you had said, well, negative 24 over 36, those are both divisible by 2. Those are both divisible by 2. Those are both divisible by 3. You could have ended up in the same spot. And that's fine. You just have to get there some way, somehow. Other questions? Oh, there it is. I don't know why mine are behind yours. All right. Number 11. We're trying to figure out what else we would have had to multiply by if 48 p to the 5th q to the 4th is our product. So it might help to multiply what you already have together. 2 times 4 would be what? 8. What else would we have to multiply 8 by to get a 48? Oh. So you should be thinking or asking yourself, 48 is equal to 8 times what? 8 times 8 is 64. 6. So part of our question mark better be a 6. We all understand where I came up with that? Okay. So next we'll go on to the p's. If we're multiplying the same bases together, what do we do with their exponents? You add them. So right now we have p to the this p is to what power? The first power. The other p is also to the first power. So we need, when we add them, we get p to the second. So what would we need our power on p to be down here if in the end we want a 5th power? 3. Okay, 1 plus 1 plus 3 is the 5th power. We need to do a similar thing for our q's. Right now we have q squared and q to the first. So we want another q to the, well, in the end we want q to the 4th. So we've already got 2 and 1. We need another what to make up 4? Another 1. 2 plus 1 plus 1 would give us the 4th. That's all they were looking for there. You're just kind of working backwards. The other way to do this, if you want more of a algebraic approach, is you could have multiplied those two things together. 8p squared q to the 3rd times question mark. And then you would have to divide both sides by 8p squared q to the 3rd. So they cancel out here. So question mark, we're still going to be left with 6. 5 minus 2 is 3. 4 minus 3 is 1. It's the same thing either way.
Are we done now?
Are we done with all our notes and our examples? We're not done yet. Number 12 should be easy peasy lemon squeezy if we were able to do number 10. 3 over 9 reduces to what? What are 3 and 9 both divisible by? 3. 3 divided by 3 is, whoa. 3 divided by 3
1.
is 1. 9 divided by 3
3.
is 3. Is this the same as having just a big 3?
No.
No, 1/3 and 3 are not the same. So you better make sure you have 1 over 3. When we divide the same base, what do we do with our exponents? Subtract them. 2 minus 1 is 1. Should that R land in the top or the bottom?
Well, it should be on the top.
Top. Bigger exponent was in the top. R should go in the top. For S, we've got 1 minus 2. We're going to have S to the
No. It's a negative, right?
negative what?
1.
Negative 1, but we don't want it to be negative, so we're going to move it to the bottom to make it positive.
Isn't it supposed to always be
The exponent will always be positive wherever the bigger exponent started off.
Okay.
So bigger exponent was in the bottom, it'll be positive in the bottom. Questions about 12?
What else did you say? I thought you had to flip it.
So if it's negative in the top, then it would be positive when you flip it to the bottom. Okay. Next one. Again, we could kind of build our answer a little piece at a time, or you could go ahead and show that you divide both sides by the 3a cubed b to the 4th. Okay, so then it cancels out and we're just left with our question mark. 9 divided by 3 is what? 3. A to the 5th divided by a cubed. When we divide the same base, what do we do to the exponents? Subtract them. We end up with a squared. B to the 7th divided by b to the 4th. B cubed. That's it. That's all we had to do. Questions about dividing our monomials? Okay, your homework is not in the book. It's a worksheet, so I will get that for you.